Good morning. This is the third part of our discussions about crystal nucleation in supercooled liquids. For short, crystal nucleation in glasses. We have seen in the previous two lectures that the classical nucleation theory does not describe the magnitudes of the crystal nucleation rates when one uses a constant value of the crystal liquid surface energy in the viscosity for the transport part. However, it does describe the temperature dependence of the overall nucleation rates as a function of the temperature. It can describe as we can see in this graph here, the log of nucleation rates, of the steady state nucleation rates versus temperature, experimental data, here the black dots for lithium disilicate glass, and the predictions of the classical nucleation theory. One way to avert this problem is to then assume that the surface energy is no longer constant, that it depends on the size of the nucleus. R is the radius of an spherical nucleus. And then this is a very famous equation by Thomson, that the size-dependent surface energy is the constant surface energy divided by 1 plus 2 delta over R. Delta is it's very complex parameters, the thickness of the interfacial layer. I mean, a crystalline nucleus embedded in a supercooled liquid matrix does not have a very sharp interface. It has some thickness, as if you recall, I have shown this in my first lecture on the molecular dynamics simulation results for supercooled germanium. They were able to measure the thickness of the interface. This is delta. Of course, you cannot measure this parameter experimentally, but it's a parameter there. You know, how diffuse is this interface, and R is the radius, considering a spherical nucleus. Anyway, there are several equations which relate the surface energy to the size of the particle. This is one of them, called the Thomson equation. And of course, the discrepancy here between the predictions of the classical nucleation theory and experimental data points is about 30 orders of magnitude for this particular system. It can be even larger, up to 55 orders of magnitude for other systems. Now, if we use now a curvature-dependent, CD means curvature-dependent or size-dependent surface energy with one adjustable parameter, and this is the one adjustable parameter, the actual surface energy for a flat interface. So we make some assumptions about delta and we consider that delta is the same as that lambda, the jump distance, 1 or 2 angstroms. We put lambda here, we place delta by lambda, and leave only sigma 0 as the adjustable parameter. Then it improves a lot, because this is log scale, so it improves a lot. Now, we can also leave 2 adjustable parameters, or 2 free parameters. We can leave sigma 0 and delta as adjustable parameters, and then the improvement is much better. Calculated is the solid line versus experimental data points. it improves a lot. It's no longer 30 orders of magnitude, but even with these 1, 2 adjustable parameters, the temperature dependence is not very well described. See, the theory underestimates here in the high temperature side of the maximum and underestimates in the low temperature side of the maximum. So even with 2 adjustable parameters, the fit of theory and experiment is not perfect. And also, now we lose the predictive ability because it's so sensitive to delta and sigma that we can fit data to the theory, but we cannot predict anything because in principle we don't know the value of this and the value of sigma. Okay, let's then see what happens with other systems. With other systems, calcium metasilicate, barium disilicate, 1, 2, 3 soda lime silica glass, 2, 1, 3 soda lime silica glass, stoichiometric glasses, the same behavior. CNT, experimental data, and CNT with 2 adjustable parameters, the same behavior. There's always a discrepancy between CNT and data. The discrepancy disappears with 2 adjustable parameters, but the temperature dependence is no longer described for all systems. Excuse me. Summary. Discrepancy between experimental and theoretical values of the steady state nucleation rate decreases considerably with curvature dependent or size dependent nucleation theory with 2 adjustable parameters. But the temperature dependence is still not perfectly described. That's the state of art. So we have been talking about in previous lectures about possible problems. What could be the possible problems of the classical nucleation theory? Metastable phases, we have checked this. They do appear in certain glasses, but do not explain the discrepancy. The diffusion mechanism, we assume that viscosity controls whatever diffusion processes are taking place during crystal nucleation. It doesn't work. We also assume that the induction times can be used to calculate the diffusion coefficients. It continues, the problem continues. It doesn't work. And then we test the surface energy. Okay, we can fit a size-dependent surface energy or a temperature-dependent surface energy. Of course, we can force fit like a temperature-dependent surface energy. And in that case, the result, and I believe I have shown this in the previous lecture, but let's recap a little bit. If we force fit, what's the value of the surface energy? The value of the surface energy to bring theory and experiment into agreement, we find out that if this is the maximum, this is the temperature of maximum steady state nucleation rates, we see that the values of surface energy to restore agreement have to increase slightly with temperature. The derivative here is very small, but it's positive, so it increases with temperature. But here, below the maximum, it has a very strange behavior. This is the strange behavior of the surface energy that comes out from force-fitting experiment and theory to agree. And as I said before, as we don't know previously this dependency, we can no longer predict nucleation rates using a variable surface energy. We can predict nucleation rates using a constant value of sigma. We somehow calculate the value of sigma, like by the famous Turnbull equation. We can estimate the value of sigma 0 of let me go back, show you here, of this sigma 0. This is the constant sigma, the sigma for a flat interface or for a macroscopic crystal. We can calculate this, well, we can estimate this by the Turnbull-Kapski equation, which reads sigma 0 is equal to alpha heat of melting divided by the Avogadro number to the power 1/3 molecular volume to 2/3. And alpha is something in the neighborhood of 0.4 to 0.6. So with this expression here, if we know the heat of melting, the volume, molar volume of a given glass forming material, we can estimate sigma and then plug sigma in the classical nucleation theory equation and get this curve here, this one. Okay, it's many orders of magnitude out, but we can predict the temperature dependence, the position of the nucleation curve. This is using a constant sigma. Predicts the temperature dependence, not the magnitude. If we want to predict the magnitude, also, we have to use this kind of form for the surface energy. But this cannot be calculated. It's just a force fitting. So the theory loses its predictive power. Am I clear? It's very important to understand these two features. Okay, so to summarize this whole story, the final missing point is, what's the effect of elastic stresses? If you recall in the first lecture, we have neglected the possible effect of elastic stresses because we assume that the crystal forms inside a supercooled liquid and then the liquid relaxes. The liquid relaxes and no longer have stresses, so they do not have any role on crystal nucleation. This is an assumption. So let's see what happens if we take stresses into account. I'm not going to show the details of the calculations because they're somewhat complex and long. If you're really interested, you can read a paper I'm going to refer to you, but I'll show you the final results of calculations taking stresses into account. These are the final results. Let's look at the whiteboard here and see if you recall now the value of the work of critical nucleus formation taking stresses into account is somewhat modified. Now, instead of delta GV square, we have to use delta GV minus the delta G strain or stress squared. So we have to calculate this part here. And this can be done, believe me. It's not so complicated, but it can be done. And then we can retest the ability of the classical nucleation theory in predicting or describing crystal nucleation rate data in certain glasses, taking stresses into account. If we do that, let's take our Drosophila, lithium disilicate. Again, there's lots of data for lithium disilicate because it's a glass that the nucleation rates, growth rates, viscosity, thermodynamic data is all available. So that's why most people use this material as a model system to understand what's going on in crystallization. So, again, steady state nucleation rate in log 10 to the power 6, power 7, 8, 9, 10. This is the kind of range where we measure nucleation rates. This is temperature. Here are the data points. See the data points of different authors. And then we have the red curve. The red curve is the typical curve that we get by using this sigma here. If we use, this is a reasonable temperature dependence of sigma. So we force fit the data points and we get this kind of expression, use it to calculate the red line, and it describes very, very well the nucleation rates up to the maximum, And then it no longer describes. It could describe if we allow sigma to vary in this way. But we don't like to do. This is strange. So we leave that part out. We use only this part here, which is reasonable. Sigma should increase with temperature. From thermodynamic grounds, we know that this thermodynamic property should slightly increase with temperature. So we use that part, calculate the curve, the nucleation curve, and this is the nucleation curve, red curve, okay? And these are the experimental data. Okay, it describes the right-hand side or the high temperature side. It doesn't describe the low temperature side because we are not using this sigma. We are using a sigma like this. We extrapolate here, and this is the sigma that we are using to get the red curve. So let me paint this now in red. So this is our red curve in that plot. Okay, now if we take stresses into account, we should have this kind of curve here. See? Taking into account the stresses and also their relaxation, because the stresses form, but they relax a little bit. They form and they relax a little bit. So if we take them into account, we should have in the relaxation this curve here. So again, because 1307 is the melting point of the stable phase lithium disilicate, 1307. If you are working with lithium disilicate, you know that this is the melting point. So we are using for the stable phase that melts at 1307. And see the blue curve here. Now that blue curve comes here, coincides with the red curve, and goes all the way to here, but doesn't describe the nucleation rates. That's my point. Even taking the stresses into account, even take into account the fact that they will somewhat relax, it doesn't change here because they relax very fast. It doesn't explain here. They don't relax so fast below TG, but doesn't explain. And we have also done this for barium disilicate. Same story. Experimental data here. The red curve comes from doing a curve like this for barium disilicate. In the blue curve, which coincides here, is taking stresses into account and their relaxation. Here they relax, so they have no effect whatsoever. There is a blue, if you look hard, there is a blue line almost coinciding with the red line. The blue line here is calculated taking stresses into account. It doesn't make any difference. It does make a difference here. It does make a difference here because then they cannot relax so fast. But does not explain the experimental data. Experimental data are here. The calculated values are here. Conclusion. Stresses do not explain the failure of the classical nucleation theory. Okay, what's the state of art then? One can use an estimate for sigma for any system. One can use the viscosity, because viscosity is a property that can be measured for any glass-forming system, at least. If the system crystallizes extremely fast, then you cannot measure the viscosity because it crystallizes before you measure. But for any decent glass-forming system, you can measure the viscosity. You have seen in previous lectures, and you have done your homework, that you can also measure and calculate delta G as a function of T from the specific heats. And then you need what? The heat of melting, delta HM, which comes here and comes here, the melting point and so on, some other thermodynamic properties, the density of the glass, the density of the crystal. With these parameters, we can plug all these parameters into the classical nucleation theory and predict a nucleation rate curve. We can predict like a nucleation rate versus temperature curve. We know that the actual magnitude could be somewhere here. But we can predict this curve, and from this curve we can take the value of T max. Okay? And that's useful. So what's the utility of the classical nucleation theory, despite the fact that it has all the problems that we have discussed in the previous two lectures and today in this introduction? I can give you one example. This is one example. If you plot then, plot the Imax. Let's say these are experimental values, and this is T max, and this value here is I max experimental, and this one is I max theoretical. We can plot the I max experimental for 51 silicate glasses that show internal homogeneous nucleation. There are 51 glasses. Some are not stoichiometric. There are maybe 10 stoichiometric systems and 41 that are not stoichiometric but show internal nucleation. If you heat them up, they will crystallize internally without adding any nucleating agent. So we can take the values from the literature, You have done this in this paper, Fouquin, Schmelzer, and myself, Journal of Non-Crystalline Solids, 2003, volume 321, page 52, and other pages. We plotted the values for several glasses. Each data point refers to one particular glass composition versus their TG. We took their TG and divided by the melting points of the crystal or by the liquidus of the non-stoichiometric systems. And we found that the nucleation rates decrease a lot with increasing TGR. TGR is just TG reduced is just the TG, say, measured by DSC, divided by the liquidus temperature of the system, or by the melting point if we are dealing with stoichiometric systems. So this is very interesting. This is some indication that, and this is log. So for some compositions here, which have a reduced TG of about 0.5, the nucleation rate is 10 to the power 15 per cubic meter per second. Whereas if you are here, around 0.58 or 0.60, the nucleation rate is only 10 to the power 1 or so, or 10 to the power 0. That's 1 nucleus per cubic meter per second. So many orders of magnitude variation. That's interesting. Maybe we can use this knowledge. This is accumulated knowledge. It took maybe 50 years to collect all these data points. You know, if you sum up all the authors that worked, they had to measure the nucleation rates and got the maximum nucleation rates for 51 systems. This is 50 years of work condensed in that single curve. We have not done all these data points. We took most of these data points from published papers. A few we have done ourselves. And then, I'm not going to give all the details, but the details are summarized in this JNCS paper. Using the classical nucleation theory, we can show the same trend. See the log, now the theoretical, I'm talking about theoretically calculated Imax. In the previous slide was experimental, now it's theoretical, follows the same trend. There is some uncertainty in the parameters, so we have a lower bound, upper bound, but it follows the same trend with TGR. the maximum nucleation rates drops dramatically with increasing TGR. From a theoretical point of view and from an experimental point of view, despite the fact that we cannot predict the actual magnitude, we can predict trends with the classical nucleation theory because we can predict the temperature dependence of the maximum. So this trend of decreasing nucleation rates with temperature is well described by theory. We cannot know for sure the actual magnitudes. You know, this whole curve could be here or could be up there, but the trend is a decreasing trend of maximum versus TGR. Now, you might be wondering why I'm talking about this. I'm talking about this because of this graph here. Qual é a dúvida?
Agora eu não lembro como a gente pôde fazer aquela curva de energia sigma em função da temperatura. A sigma de DeMA.
Para fazer, você tem que fazer um force fit, ponto a ponto. Você pega esse ponto experimental aqui e calcula qual o valor de sigma para coincidir. Pega esse ponto, qual o valor de sigma para coincidir. Pega esse, qual o valor de sigma para coincidir. Dá isso. É force fitting mesmo, é ponto a ponto. Okay, so I was talking about all these features of the nucleation theory because we can now do a very neat kind of plot. Very neat. We can put Tmax versus the divided by the melting point, Tmax divided by the melting point versus TGR, Tg over the melting point, Tmax versus TGR, from 0.5 to 0.75. Almost, I would say 99% or more of all glasses, at least inorganic glasses, have reduced Tg between 0.5 and 0.75. You'll find half a dozen which are a little bit below and half a dozen a little bit above. But 99% of glasses, the Tgs are in this range. So let's see what happens if we now calculate. You can get a glass like your glass and you know what's the TGR is for your glass. You can calculate Tmax using the classical nucleation theory. Or you can even pick the experimental data if your glass shows internal nucleation. If we plot all this, and you can see in this paper, Isothermal and adiabatic nucleation in glass, Journal of Non-Crystalline Solids, 1987, that I published many years ago. All glasses that show internal nucleation, that's the glasses that you guys and ladies are working for your homework, have the maximum nucleation rates above Tg, because this straight line here is the straight line for which Tmax is equal to Tg. All of them have Tmax at or slightly above Tg. And not only that, all of them have a TGR below 0.6. Now I'm using here experimental data because they show internal nucleation, so I can use measured data. I can use measured data. Now, if I come here, glasses which have a TGR higher than 0.6, they only show heterogeneous or surface nucleation in laboratory time scales, so we cannot measure. But we can calculate. We can still calculate where their maxima would be, in which temperature their maxima would be. And if you look here, take like B2O3, GO2, silica, albite, sodium disilicate, lead metasilicate. There are many, many, many glasses that do not show internal nucleation. Their maxima are below TG. And that's why they don't show internal nucleation in laboratory time scales. Since their maxima are below TG, the induction times are very long and the nucleation rates very small. If you remember now, I'm going to show the previous plot. Here. Oh, sorry, this one. If their TGR are very high, TGR is high, like say 0.7 or 0.65, the nucleation rates are very small. So you cannot measure. They're too small that we cannot measure. You have to wait for years or have a sample of the size of this room and be patient for 1 or 2 or 3, half a dozen of nuclei to form. And this is very interesting. We are seeing a very practical outcome of this, despite the fact that the nucleation theory is not perfect. But we can use it to produce this plot here. You can take any glass forming system and at least calculate the Tmax. And I bet if you do that, because I have done for several systems, not for all, but for several, if the TGs are above 0.6, their Tmax will be below TG, then the nucleation rates, the homogeneous nucleation rate will be very small to be measured. Also, the induction times will be very long because they are below TG. This is a very practical use of the theory. Calculated, no? As I said, these are calculated Tmax, these are measured Tmax. But we can also calculate, if we calculate this Tmax here, they'll be about here. The calculated Tmax will coincide more or less with the measured Tmax. I actually have done this. Summary. The classical nucleation theory using viscosity and sigma zero, viscosity, measured sigma zero, measured viscosity, calculated sigma zero with this expression, predicts that the maximum values of the steady-state nucleation rates, Imax, diminish with increasing TGR. This prediction was confirmed by experiments. As a general conclusion, silicate glasses with a small TGR, say as a rule of thumb less than 0.6, show internal nucleation in laboratory time scales. In the other glass and vice versa, glasses with a TGR larger than 0.6 only show surface or heterogeneous nucleation. To produce glass ceramics with the other glasses, you have to put some nucleating agents. Zirconia, noble metals, titania, P2O5. Every glass demands a different nucleating agent and a different quantity of nucleating agent. A few glasses that have TGR smaller than 0.6, they don't need any nucleating agent to show internal nucleation. This is a very practical outcome. Let me see if I have something else on the nucleation theory. This is just a summary. Let me see. Well, just for fun, just to summarize, to finalize this lecture, which will be shorter today because we have to work on your tests. We are going to mark and correct all your tests today in the next 5 minutes or so. So we have done a fun and very educative kind of work. We took albite. Albite is sodium aluminum silicate. Albite is one of the most stable glass, at least of the oxide glasses, known to man. Extremely, extremely, extremely difficult to crystallize. People have made albite. They left albite samples in a glass furnace above TG for 5 years. It did not crystallize. Why is that? What's the secret behind this tremendous stability of albite glass, also B2O3 glass and other glasses? We calculated where would the homogeneous nucleation rates of albite be. And these are the results. The blue curve and the green curve refers to calculations. And they are slightly different because there are several expressions for viscosity. There are several values for alpha. It can be 0.4, 0.5, 0.6. So you have to play games a little bit with these quantities because you don't know for sure what's best to describe the nucleation rate of a certain glass. So we have some uncertainty, but varying within reasonable ranges, we have this estimate here, somewhere here. But the TG of this glass, the TGR, is almost 0.78, almost 0.8. So the predicted curves are much below TG, well below TG. And that's why this glass does not show any sign of homogeneous nucleation. You heat it up, there's no nucleation, then there's no growth. Now, if now you make some calculations, changing the surface energy, if you recall, heterogeneous nucleation is due to the fact that the surface energy can be decreased by some catalyzers. Then we changed the surface energy, so it came here, still below TG. We changed a little bit more. This is in the computer. The surface energy. And there you you need a very powerful nucleating agent to bring the nucleation rate curve to be above the TG. It doesn't work if we only seed. We can seed it with some other nucleants that are not so powerful, so that curve is still below TG. You need a very powerful nucleating agent, and this is a powerful one. Then you actually bring the nucleation rates above the TG, and now you can measure. And people have done experiments. They took albite crystals. Albite is a mineral which can be crystallized under high pressures, in geological time scales. So they crushed albite crystals, they seeded an albite glass with albite crystals on the surface and heat it up. Then it crystallized because they found a very powerful seeding agent. And then albite glass crystallizes. So this is the kind of exercise that one can do using the classical nucleation theory in measurable parameters. Understand the reason why certain glasses crystallize so fast or certain materials crystallize so fast while others are very reluctant to crystallization. We have also done similar experiments for B2O3, and the same explanation applies for B2O3 and other reluctant glass formers. So the theory can be used to design experiments or to design materials that are reluctant to crystallization. Sometimes you want materials that are very reluctant to crystallization. For instance, can you think of an example? Give me an example where you want a glass that does not crystallize. Okay, metallic glasses, for instance. Metallic glasses, the whole community is crazy to avoid crystallization because most metallic glasses crystallize so fast that you cannot produce a glass. No, metallic liquids crystallize so fast, so they're always looking for ways to avoid crystallization, to mix a lot of atoms and some strategies to minimize crystallization. But give me another example. Biosilicate.
No,
pure silica. But pure silica, yes, so pure silica is one example. If you want to make a silica glass, and pure silica glass is very sensitive to like sodium oxide and water, so you have to eliminate sodium oxide and water. Another example is glasses for nuclear waste encapsulation. You know that nuclear wastes, one way to encapsulate them is to melt these radioactive wastes, make them into a glass. You add some silica, some boron oxide, and melt the whole thing, so you make a large chunk of glass, and then you bury that large chunk of glass to avoid contamination in the air. But during radioactive decay, there's heat evolved. And if this glass is not very stable, it will crystallize in a very uncontrolled way and will crack. Because glasses, when they crystallize or they devitrify, that's uncontrolled crystallization, they may crack. And then the radioactive materials will be released. So that's one example. Or sometimes, like one of the bioglasses that we are working in this lab, called F18. 18 because we had 17 trials. So F18 was the 18th trial that developed by my former student Marina. It's very, very stable against crystallization. So it allows us to pull fibers before they crystallize, bioactive fibers. And I just read a very interesting example. Some medicine, these are organic materials, but they are glassy. Lots of medicine, organic medicine, are glassy. They are vitreous, organic materials. Because being vitreous, it's easy for us, humans, to digest them. You have to digest, and they dilute, and they go to the blood, and so on, and act on some kind of diseases. Now, some of these materials, they lose their validity. You see, when you buy a medicine, there's the validity, half a year, 1 year, or so on. You know why? Several of them in the atmosphere, they absorb a little bit of water and so on, CO2, and they crystallize. When they crystallize, they are no longer soluble, and they lose their validity. So many people in the medical area, they work with not only on the chemical principles of their medicine, but they add a lot of extra stuff there, substances, to make a very stable vitreous material. This is very important. Okay? So, this is a summary. Despite all the problems that we have discussed during 3 lectures, and there are many others that I have not discussed, classical nucleation theory can be a useful tool to estimate Tmax. And this is a useful guide to review the nucleation mechanism, to understand or to evaluate the nucleation processes in glass-forming materials, and also for the design of crystallization or stabilization heat treatments. Sometimes you want to crystallize a material, sometimes you want to stabilize a glass. In any case, it's very important to understand and control crystal nucleation. Questions? No questions. Okay. Thank you very much. See you next week.